So we'd like to work some exercises with diagonalization. So something very practical. And we've done quite a lot of theory, a lot of very rich theory in this section. So here's the exercise type that we want to do. So here we have a matrix A is diagonalized. It's already diagonalized for us in the form A PDP inverse, right? That's the form that diagonalization takes. A is similar to a diagonal matrix via P, right? A is equal to PDP inverse. Use the construction used in the diagonalization theorem to find the eigenvalues of A and a basis for each eigenspace. Okay, so here we have right here, this is basically our matrix A, right? And this guy is our P. And then in blue, we're going to have our D. That's our diagonal matrix. And over here on the right, we have P inverse. That should be the inverse of P. So it's already been factored in that form for us, right? A's been factored into PDP inverse. Now remember, for the construction of the diagonalization theorem, your eigenvalues show up in matrix D, right? Your eigenvalues are the diagonal entries, right, along this diagonal matrix. So your first eigenvalue would be 4, sometimes called lambda 1. I'm just going to call lambda equals 4. The second eigenvalue would be lambda 2, lambda equals 3. So when you're proving the diagonalization theorem, in the construction, your D consists of the eigenvalues down that diagonal. Okay. And when you're constructing P, each column of P is an eigenvector that corresponds to an associated eigenvalue. So we want to do a basis for the eigenspace of A, first of all associated with 4, right? 4, that was our first eigenvector. So our first eigenvector here is 4, that shows up. So that means the first column of P, that's the first column of P right here. It's not writing. That first column of P is going to go along with the 4. So a basis here, I'm going to call it B for basis. It's the set containing that first vector, 1, 1. So the eigenspace of A associated with the eigenvalue 4 consists of just that first column vector in P, 1, 1. Then you got to do the same thing for the second eigenspace. You're going to have a basis for the eigenspace of A associated with 3. So notice that 3 was your second eigenvector, right? It was the second diagonal entry. So you're going to take your second column then, your second column, right? 1, 2, and that'll be a basis for the eigenspace of A associated with 3. So we're going to write basis for eigenspace associated with 3 is going to be, I'm going to call it something, I'm not going to call it B, I'm going to call it E. Script D, I'm having trouble today writing my script D's. Come on, there we go. Script D, that's the set containing which vector? Which vector was that? 1, 2. Okay, so based on that factorization of A, we can immediately find the eigenvalues of A, 4 and 3, and we can find the eigenvectors for each of those eigenvalues just by looking at that P matrix, right? The first vector and the second vector. These are actually bases for those eigenspaces. All right, let's do another example. Scroll a little bit. So number 2. Let's say I got a 3 by 3 this time. So my A is going to be 1, 2, 3, 3, 0, 3, 3, 2, 1. This is my matrix A. And let's say that factors into a PDP inverse, such as 3, 2, 3, 0, 1, negative 1, 1, 0, 1. That's my P. And then my D is going to be 6, negative 2 down the main diagonal. And then zeros everywhere else. And then P inverse over here, see if I can squeeze that in, it's going to be 1/8, negative 1/4, 5/8 down the first column. Second column is going to be 1/8, 3/4, negative 3/8. And down the third column, we're going to have 1/8, negative 1/4, negative 3/8. So here we have A, and then we have P, and then we have D, our diagonal matrix, and then P inverse. This is called the diagonalization of A, or the diagonalization factorization of A, it's sometimes called. Okay, so what do we want? We want the eigenvalues of what? Eigenvalues of A. So first we're going to find the eigenvalues of A just by looking at that factorization. So I'm going to have 6, all right, lambda equals 6. And then we got this negative 2, right? Lambda equals negative 2. Now negative 2 has multiplicity 2. I'm going to write that down. Multiplicity of negative 2 equals 2. It's repeated, right? It's a double eigenvalue here. And something special happens there. Okay, so we got to find bases for two eigenspaces. Basis for the first eigenspace is going to be the eigenspace of A associated with the first eigenvalue, 6. So since there's just a multiplicity 1 right here, right? 6 has multiplicity 1. You're just going to take the first column vector in P to be your basis for your eigenspace here. So I'm going to write my basis B consists of the following single vector. It's 3, 2, 3. All right, now I got to find a basis for the eigenspace associated with negative 2, the eigenvalue negative 2. So we're going to call this basis for the eigenspace of A associated with eigenvalue negative 2. Now the interesting thing here is that negative 2 had multiplicity 2, right? Negative 2 showed up twice here, right? Showed up here twice. So what I'm going to do, I'm going to take both of these second vectors in P to form my basis. So we're going to actually have a two-dimensional vector space here. So our basis, there should be two vectors in our basis. What were they? 0, 1, negative 1, and 1, 0, 1. So my basis here, I'm going to call it script E. It's going to consist of what? 0, 1, negative 1. It's the second column of P. And then 1, 0, negative 1. That was the third column of P. So it's a two-dimensional vector space. So all the vectors in that eigenspace can be built from those two eigenvectors, basically. Okay. So some nice little results. Not really results, more practice problems. Doing some practice. Here is a result that is useful. Nothing big, it's kind of a smaller result, but it's useful. If A is similar to D via P, so if A equals PDP inverse, then A to the K is equal to P D to the K P inverse. Let's prove that. It's really simple to prove. Some very simple algebra. proof. So we're going to suppose A is similar to P, right? A equals PD, P inverse. Then we're going to raise the left-hand side to the kth power, right? The kth power. That means we have to raise the right-hand side to the kth power. So we're going to have PDP inverse. In parentheses, all that's going to be raised to the kth power. So what does that mean if we raise something to the kth power? It means we multiply it together a bunch of times, right? We're going to have PDP inverse. It's going to be our first factor. Then we're going to have PDP inverse. That's going to be our second factor. We're going to do this a bunch more times. You're going to have PDP inverse a bunch of times, right? You're going to have K factors here. K different factors. K factors. And if you notice carefully, essentially the P inverse and the P is going to cancel. And then this P inverse is going to cancel with the P in here. And this P is going to cancel with the P inverse that comes before it. So all the P inverse P's that are next to each other are going to cancel. Or they're going to become identities. So we're going to have, this is equal to what? P bunch of D's, dot, 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 and P inverse. Now the question is, how many D's do you actually have? How many factors of D do you have in here? You're going to have K factors still. If you write that out properly, that's going to give you what? P, D to the K power, and then P inverse. Yeah, so in short, if A is similar to D, then A to the K equals P, D to the K, P inverse. That's sometimes useful for doing quick computations. Making your computations easier. Let's do an example or two of that. Here's an exercise. A matrix A is diagonalized in the form A equals PD, P inverse. Compute the following. Number one, we want to find -4, 3, 6, 5, that matrix raised to the 9th power, given the following diagonalization of A. So -4, 3, 6, 5. This is your A. This is of the form 1, 1, 2, 1 multiplied by 2, 0, 0, -1 multiplied by -1, 1, 2, -1. Okay. So this here is our A, right? And then in blue here we have our P. I should have put that in green, right? P. Yeah. In the middle you got your D, that's your diagonal matrix. And then on the far end you got your P inverse. So, what are we after? We're after A to the 9th power, -4 to the 3rd power. -4, 3, 6, 5. To the 9th power, well, that's going to be what? P, D to the K, P inverse. So we're going to have what? 1, 1, 2, 1. So the P doesn't change. But then we're going to have D to 0, 0, -1, to the kth power, which is 9 here, to the 9th power. Then you're going to have P inverse, which we have here is -1, 1, 2, -1. So this makes your computations a lot easier. You just copy down the green matrix, 1, 1, 2, 1. And then you raise your blue matrix to the 9th power. So when you have a diagonal matrix, it's really easy to raise it to the 9th power. That just means you multiply the matrix by itself 9 times, which when you have a diagonal matrix, it's just going to be 2 to the 9th power. 2 to the 9th power here is 512. And then the next diagonal entry, -1 to the 9th power, is going to be -1. And then you have that last green matrix on the end. -1, 1, 2, -1. So, now what you can do, you can multiply the first two matrices together. Let's do matrix multiplication. We're going to leave the green matrix there on the end. -1, 1, 2, -1. So how do you multiply matrices? So you do the dot product of the first row with the first column. You're going to have 1 times 512 is 512, plus 2 times 0 is 0. So we get 512 for the first entry. All right, so for the first row, second column, all right, second row, second column, let's see, get this to work. And a dot product, first row with the second column, first row with the second column. I'm going to do 1 times 0 is 0, plus 2 times -1 is -2. All right, now we want the second row, first column, second row, first column. So I'm going to take the second row. That's not good, it's erasing my stuff. Second row and first column, we're going to take 1 times 512. We're going to get 512 plus 1 times 0 is 0. All right. And then we're going to get the second row, second column. So here we go. We got the second row, second column. Take the dot product. You got 1 times 0 is 0 plus 1 times -1 is -1. All right. Now I can multiply these two matrices together. 512 times -1, so it's the first row, first column is -512, plus -2 times 1 is -2. All right. Now let's do the first row, second column, first row, second column. 512 times 2 is 1024, plus -2 times -1 is +2. All right, now let's go into second row. We're going to do second row. Please. Thank you. Second row, first column. We're going to do what? 512 times -1 is -512. Plus -1 times 1 is -1. All right, and then we're going to do the second row, second column. It's going to be 512 times 2 is 1024, and we're going to do -1 times -1 is +1. Let's combine these together, and we're going to get the following matrix. What is it? -514, -513, 1026, 1025. So that's a really nice way to do that nasty -4, 3, 6, 5 to the 9th power without having to actually multiply that out 9 times, right? We didn't have to multiply that red matrix out 9 times. Yeah, we used the diagonalization. It was much easier, right? All right, let's do one more. The diagonalization really helps. So I want to find what is 2, 1, 1, 0, 1, 0. 1, 1, 2 to the kth power when 2, 1, 1, 0, 1, 0, 1, 1, 2 is equal to the following. I think I don't have enough room. I need to write it down below. Yeah, I just don't have enough space here. When it's not working. When 2, 1, 1, 0, 1, 0, 1, 1, 2 is factored in this diagonalization form. 0, 1, 0, -1, 0, 1, 1, 1, 1. 1, 0, 0, 0, 1, 0, 0, 0, 3. You can see that's our diagonal matrix. The D, we got what? -1/2, -1/2, 1/2, 1, 0, 0, negative 1/2, 1/2, 1/2. So basically here we have first our A, then we have here, that should be green, right? Our P, then we have our diagonal matrix D in the middle, that's the blue, and the P inverse is there on the end. All right, so we want this red matrix raised to the kth power. That's what we want to do. So we're not actually given a number, just the kth power in general. 2, 1, 1, 0, 1, 0, 1, 1, 2. And we're raising it to the kth power. Okay, so that's going to be equal to our P matrix, 0, 1, 0, negative 1, 0, 1, 1, 1, 1. Then we're going to have our D matrix, 1, 0, 0, 0, 1, 0. 0, 0, 3, and that's going to be raised to the kth power. So we're going to put a little red k power up there. That's what our theorem said, and then we just write down our green do, negative 1/2, negative 1/2, positive 1/2, 1, 0, 0, negative 1/2, 1/2, 1/2. I think that's what that was, that green matrix. Let me scroll up. Can't see the tops. Yeah, that's right. Okay, so the first thing doing here, copy down the green matrix. Don't deal with it. We're going to deal with the blue matrix right now. We're going to raise stuff to the kth power. What does that mean? I'm going to have what? 1 to the k is going to be 1. 1 to the k is going to be 1. And 3 to the k is just going to be 3 to the k. Everything else is going to be 0. That's the way you do diagonal matrices. So you got 1, 1, 3 to the k down the main diagonal. And then you got the green stuff. Negative 1/2, negative 1/2, positive 1/2, 1, 0, 0, negative 1/2, 1/2, 1/2. All right, now we're going to multiply the first two matrices together, the green and the blue. And we're going to leave that second green matrix alone. Negative 1/2, negative 1/2, 1/2, 1, 0, 0, negative 1/2. 1/2, 1/2. We're just going to do some matrix multiplication between the first green and the blue. All right, let's think. I'm going to do what the first row and the first column dot product. We're just going to have a 0 times 1, 0. Negative 1 times 0, 0. 1 times 0, 0. So we get 0. All right, first row, second column. So have 0 times 0, 0, plus negative 1 times 1 is negative 1, plus 1 times 0 is 0. So I got negative 1. All right. First row, third column. Dot product. All right, 0 times 0 is 0, plus negative 1 times 0 is 0, plus 1 times 3 to the k is 3 to the k. There we go, we got a 3 to the k. All right, now let's go in the second row. Second row, first column. Not writing. There we go. 1 times 1 is 1, 0 times 0 is 0, plus 1 times 0 is 0. Okay, way to go 1. All right, second row, second column. One times 0 is 0, plus 0 times 1 is 0, plus 1 times 0 is 0. We got a 0 there. All right, second row, third column. One times 0 is 0, plus 0 times 0 is 0, plus 1 times 3 to the k is 3 to the k. Okay. Ouch, my back's hurting. All right, what are we doing next? The last row, third row. All right, let's see. Taking the third row, I'm going to dot product with the first column. 0 times 1 is 0, plus 1 times 0 is 0, plus 1 times 0 is 0. I just get a 0 there. All right, third row, what, second column? Ouch, my back. 0 times 0 is 0, plus 1 times 1 is 1, plus 1 times 0 is 0. So I get a 1 there. All right, we're going to do the third row and the third column dot product. 0 times 0 is 0, plus 1 times 0 is 0, plus 1 times 3 to the k. 3 to the k. All right, so we're done with that. Let me just think a second. Looks good. Now let's multiply these two matrices together. Let's see, first row, it's not working. There it goes. First column. 0 times negative 1/2 is 0. Negative 1 times negative 1/2 is 1/2. Plus 3 to the k times 1/2 is 1/2, 3 to the k. All right, so we got something weird there. Let me make some more space. I think we're going to run out of space here. All right, let's go on the first row, second column. Thank you. All right, dot product. 0 times 1 is 0. Negative 1 times 0 is 0. 3 to the k times 0 is 0. Yay, we got a 0. Easy work. Okay, can we get to this third column now? First row, third column. There we go. Please. There we go. 0 times negative 1/2 is 0. Negative 1 times 1/2 is negative 1/2. And 3 to the k times 1/2 is 1 to the half times 3 to the k. That should be a plus right there. Yeah. All right, now we're going to the second row entries. Second row entries, if I can get this erased. There it goes. Second row, first column, we're going to get 1 times negative 1/2 is negative 1/2. 0 times negative 1/2 is 0. And plus 1/2 times 3 to the k is 1/2, 3 to the k. All right, let's go to second row, second column now. See if I can get this to work. There it goes. Have 1 times 1 is 0. No, 1 times 1 is 1. 0 times 0 is 0. And 3 to k times 0 is 0. So I'm just going to have a 1 there, right there in the middle. Just a 1. All right, let's do second row, third column. There it goes. Second row, third column. 1 times negative 1/2 is negative 1/2. 0 times 1/2 is 0. 3 to the k times 1/2 is 1/2 times 3 to the k. All right, so now we're on to the third row. Figuring out the third row. Get rid of that, get rid of that. All right, can I get the third row here? There it goes. Third row, and let's do the first column. 0 times negative 1/2 is 0. 1 times negative 1/2 is negative 1/2. Thank you. Plus 3 to the k times 1/2 is 1/2 times 3 to the k. All right, so now we're going on to the, what is it called? Third row, second column. There it goes. Okay, there it goes. Dot product. 0 times 1 is 0. 1 times 0 is 0. 3 to k times 0 is 0. Ah, we got another 0. Yay, yay, yay. All right, here we go. Third row, second column. Third row, third column, rather. Third row, third column. There it goes. 0 times negative 1/2 is 0. Plus 1 times 1/2 is 1/2. Plus 3 to the k times 1/2 is 1/2 times 3 to the k. Now, there we are. That's it. That's pretty much it. Oh, I don't need this 0 here. That's your answer. Now, if you want, no, we'll just leave it like that. We'll just leave it like that. I was going to say you can simplify things a little, but that's it.